Okay, Devashish, can you hear me? Yeah, I suppose you can hear me. And so let's start. So what did we do last time? Last time, we didn't have an arbitrary P field K. We had a finite extension of QP. And if we denote by E, the ramification index of K over QP, and we will denote by E1, or sometimes even, it will also be called E1K if we want to specify which field we are talking about. So E1 is E divided by P minus 1. Our prime P is fixed, and the field K has ramification index E, and E1 is E divided by P minus 1. And let's denote by zeta a primitive pth root of unity, right? And we were interested in finding out what the structure of this field is. This field, it's not a field, it's a vector space over Fp, along with its filtration. What is the structure of this quotient, k star modulo k star to the power p, along with its filtration? The filtration is given by U1, U2, etc., right, on k star, and it has this image filtration in this quotient. So what we had proved last time was that if zeta is in K, if K contains a primitive pth root of unity, then of course this E1 is a natural number. I mean, a priori it's just a, what is it? It's a rational number, right? A priori it's just a rational number. But if zeta is in K, then it's actually a natural number. And this k star modulo k star to the power p, whose structure which we want to determine, let's call it U naught bar. Just another notation, because the other subgroups are going to be U1 bar and UI bar. So what is UI bar? Is the image of UI in excuse me, k star modulo k star to the power p. And what is UI? UI is 1 plus pki. So these are units which are congruent to 1 modulo the ith power of the maximal ideal. So you have U1 bar and U2 bar, etc. What we had proved was that UPI bar is the same as UPI plus 1 bar for every I going from 1 to E1 minus 1. This is E1 minus 1. But when I is equal to E1, I don't have equality here. I have an inclusion, and this group is trivial, right? Whereas this UPE1 bar is of dimension 1. And in fact, it can be made isomorphic to FP if I choose zeta. Zeta is a primitive pth root of unity. There are many of them. If you make a choice, then you get an isomorphism, right? In general, by Kummer theory, cyclic extensions of degree p of a field containing a primitive pth root of unity correspond to lines in the FP space k star modulo k star to the power p. In this case, our field is a p field. It is a distinguished cyclic extension of degree p, namely the unramified one. And the question could be asked, which line does it correspond to? And the answer is that it corresponds to this line, UPE1 bar. So in some sense, it's the deepest line in the filtration. It's the one which is the lowest or highest, or I think it should be called the highest maybe. Anyway, so it's the deepest line in the filtration. If I have some line which is in UM bar, but not containing UM plus 1 bar, then the unique ramification break of this cyclic extension, which corresponds to D, occurs at PE1 minus M. This is for M. M is allowed to be what? Yeah, M is allowed to be 0, but it's not allowed to be PE1. Okay. If M is equal to PE1, then of course this D will have to be equal to UPE1 bar, because there's only one line, right? This is of dimension 1. And the unique ramification break occurs at -1, because it gives you the unramified extension. So if you call it T in general, then T is -1 in this case, but T is equal to PE1 minus M in general, if M is from 0 to PE1 minus 1. And as I said, we have this parametrization of all cyclic degree P extensions of K. They're parameterized by FP lines in this field, not field, in this quotient, K star modulo K star to the power P. So I've used several other notations. I've used this notation, and I've just now introduced this notation as well. So these are just different notations. You don't have to prove anything in order to establish these equalities. Now, what happens if lambda is zeta, this primitive pth root of unity zeta, is not in K? We didn't give any parameterization of the cyclic extensions of degree P. And in fact, we don't even know whether there are any cyclic extensions of degree P in this case or not. In this case, we can compute the dimensions of these things, right? What is it? Here, the dimension, the codimension is Fk, right? The codimension is Fk here, the codimension is 1. So we know the dimensions of these spaces. This one, we know the dimensions of all these spaces. So we know how many degree P cyclic extensions there are, because we know how many lines there are in these spaces, right? But if zeta is not there in K, we don't have Kummer theory. At least we don't have the usual Kummer theory. There's a modified version, which is what we are going to talk about today, in fact. So we need to do such a thing, because as such, we don't even know whether this K, which doesn't contain a primitive pth root of unity, has any cyclic extensions of degree P at all. But what we had proved last time was that if there is some extension which is cyclic of degree P, and if T is the unique ramification break of the Galois group, then of course T is -1 if this is the case if L over K is unramified. Okay, let's say that we do know one cyclic extension of degree P, namely the unramified extension. Okay, we just know that one. But are there any others? What we are saying here is that if there are some others, then the unique ramification break T will have to occur at some integer. I mean, T will have to be prime to P, and between 1 and PE1 minus 1. Okay. Here, the ramification breaks. This was when zeta is in K. The possible ramification breaks are -1, the integers in 1 to PE1 which are prime to P, and PE1 itself is a ramification break, right? This was the case when the line is in U0 bar, but not in U1 bar. But this PE1, even if it's an integer, is not a ramification break when zeta is not in K. So today what we want to parameterize cyclic extensions of degree P over K, even when zeta is not in K. And to compute the contribution of these to Sayre's mass formula. That amounts to computing the unique ramification, the number of extensions of with a given ramification break, and so on. So let's get started. Now, it so happens that there's some purely algebraic results which we need and which are useful in many other places as well. So let's start with these algebraic preliminaries. So take P to be any prime and take F to be any field of characteristic different from P. Okay, so we are not looking at a P field. We will apply these results to P fields of characteristic 0, of course. Can't be P fields of characteristic P because the characteristic of the field has to be different from P. And then this F may or may not have a primitive pth root of unity, but we adjoin 1 if it doesn't have 1 and call it K. So K is F zeta, where zeta is a primitive pth root of unity. So this is going to be a Galois extension of F. Let's call it delta the Galois group, and it's going to be a subgroup of the of ZP, Z mod P Z star, right? In fact, instead of just considering it as a subgroup, we think of the character omega, meaning the inclusion, let's call it omega, and it's called the cyclotomic character. So basically, it's if you are thinking of this as an inclusion, then omega is, omega is just another name for that inclusion. Okay, so what is this omega? This is the one which gives the action of delta on, what is it? K star P. This is a group of order P. So the automorphism group of any group of order P can be identified with FP star. That's why you get this inclusion here. You get this inclusion or this cyclotomic character. Anyway, so this delta acts on the additive group, the multiplicative group, and the multiplicative group modulo pth powers. So this is what we are going to look at, the action on pth powers. K star modulo pth powers. So if I have a cyclic extension of degree P of my field F, then this is, here is E and here is this K. I can always form the compositum EK. This is of some degree. This is of degree P, cyclic. And this is also cyclic, but I don't know the degree. All I know is that the degree divides P minus 1. So E over K, EK over F is an abelian, or actually, in fact, a cyclic extension of K of degree, whatever this degree here is, let's call it D. then it's going to be d times p, right? So this is ek. I mean, you join zeta, and this is of course going to be cyclic of degree p, and this is going to be cyclic of degree d. Now look at this part here. Zeta belongs to k, so this extension ek, which is cyclic of degree p, corresponds to a line d in k star modulo k star to the power p, corresponding to this cyclic extension of degree p. So what have I done? I have E over F, which gives me E k over k, which gives me a line in k star modulo k star to the power p. That's the summary. Okay, and of course, as I said, this D acts, it's not D. The Galois group is called delta. So the Galois group delta acts on this FP space. And the first lemma says that this line D is delta stable. So what it means is delta stable means that sigma times x belongs to D whenever sigma is in delta and x is in D, then sigma times sigma of x is again in D. That's what it means to be delta stable. And if delta is acting on some FP line, then it has to act through some character. Some character chi from delta to FP star. Because this is, as I just said, it's the automorphism of the group of automorphisms of D. Okay, and the second part of the lemma says that delta acts on D through omega. So that's the thing. And this is the proof. So let's look at why. So take an A such that A bar generates D as an FP line, right? But as a group, I mean, it's the same. Then if I denote by X a pth root of A, then this E zeta is just Kx, right? E zeta is also another name for E zeta is EK. Now, what is sigma of A bar? That is by definition sigma of A bar for every sigma, because that's the action, the delta action on K star bar, which is K star modulo pth powers, is derived from the delta action on K star, right? So that's exactly what is being said here. So let's look at Kx. By definition, it's F. You first adjoin zeta to obtain K, and then you adjoin X, which is a pth root of this particular A. Now, let us choose, but this Kx over F is also, it's cyclic, it's Galois, right? And this here is K and here is delta and here's sigma is an element of delta. So I can choose an automorphism sigma tilde of an F automorphism of Kx, sigma tilde, which maps to sigma, right? Because delta is a quotient of this Galois group. So for every lift sigma tilde, Kx is stable under the action of this sigma tilde, right? So this is what I've written here. Okay. And what is sigma tilde of zeta? Sigma tilde of zeta is, of course, just the same as sigma of zeta, because zeta is in K, and sigma tilde restricted to K is equal to sigma, right? So this calculation, kx is also k of sigma tilde of x for any sigma tilde. Now, when I raise this sigma tilde of x to the pth power, of course, that's sigma tilde of the pth power of x, but the pth power of x is a. So sigma of a bar belongs to D. Why is that? Because if there's the only elements of sort of, that's because basically what's the kernel of k star modulo k star to the power p. Sorry, I wanted to write, yeah, k star is okay. L star modulo L star to the power p, where L is this k root D, the kernel is equal to D. Okay, so if there's something else, sigma tilde of x, whose pth power is in k, that means that what am I trying to say? Yeah. That's right. Yes. So it means that this sigma of A would be in the kernel of this map, and therefore this sigma of A bar has to be in D. Okay. So that shows that D is delta stable. Now let's compute the character through which delta acts on this D. Okay, so let me denote by delta a generator, by tau a generator of delta, and by G a generator of this Galois group here. If I've chosen a primitive pth root of unity, then and a generator x, x is pth root of A is in k star, which generates, this A generates D, right? That's a notation. So I can take the sigma is a generator. It's not sigma, it's G. This is a generator of kx over k. Now I don't know the character through which it acts on D, so let's call it eta. Let this be the character through which delta acts on D. So by definition, tau of A is b to the power p times a to the power eta tau. And this can be written as tau tilde of x is b times x to the power eta tau for some b in k star. So now you just do this computation and you will see that, so basically what you're doing is you are computing two things. You are computing tau tilde of g, the action of this on x on the one hand, and you are then computing g of tau tilde x. It turns out that they have to be equal because this, the Galois group of kx over not only k, but over f is commutative. Okay, so the two computations were, this is the first, this is the second result. So if you compare them, you'll have these b's which will disappear, and these x to the same powers disappear. So here you'll get zeta to the power omega, and here you'll get zeta to the power eta. And therefore this omega has to be equal to eta. This is the character through which delta x on D, and we have proved that that character is the cyclotomic character, which is what we wanted to prove. Yeah. Okay, there is a sort of converse to it. So what is one direction? The direction is uh, it was E over F, cyclic degree P. Then you get a line in K star modulo K star to the power P. So this is delta stable FP line. This is what a cyclic extension of degree P like this gives rise to, right? This is what you have done. Conversely, if we have a delta stable FP line D, oh yeah, okay, there was another thing, delta stable FP line, on which delta acts through omega. Now, conversely, if you have such a thing on which delta acts through omega, then there's a unique degree P cyclic extension E over F such that this K root P of D, I mean, this is a cyclic extension of K, is obtained from E by just adjoining a primitive pth root of unity. So now we have to prove this converse. In other words, we have given a map. Cyclic degree P over F to lines in K star modulo K star to the P on which delta acts through omega. We have given a map. I mean, this is a map. And this, the next lemma says that it's actually a bijection. Okay. So suppose we have a line D on which delta acts through omega. The first thing we claim is that, of course, this K root, pth root of D, it's a cyclic extension of K, but the claim is that it's Galois over F. Of course, this notation, K pth root of D, stands for K you adjoin X, where X is a pth root of A, and A is a generator of D. More precisely, A is in K star, and its image A bar is in D, and it generates D. Okay, so how do we show such a thing that that's Galois over F? So something is Galois over a field if it contains all the conjugates of every element that it contains, right? It's all separable and everything. That's not a problem. So you need to check that it's normal, as it's sometimes called. So we need to show that if I have a conjugate, and the conjugates of A are sigma A for some sigma in delta. So conjugates of X are going to be pth roots of conjugates of A. So I need to show that the pth root of every sigma A is also in Kx. Okay. What is sigma times A? Sigma times A is, by definition, some up to a pth power of an element of, up to the pth power of an element in K star, it's A to the power omega sigma, right? Because that's how, that's what is given to us, that, sigma, or rather sigma maps D to D, and it takes any A bar here to A bar to the omega of sigma. And you just take the pth root. This is a pth root of sigma A in your field. So Galois over F is easy. but we have to prove that now we are claiming that it's actually commutative. So that again, I mean, it's not a very complicated computation. So it's Galois, then if the generator tau of delta will have a lift tau tilde, what does it do to x? We have computed the result, it's something like this. And G is a generator of this kx over k is generated by some G, which takes x to zeta times x, right? Now you compute the tau tilde times G, I mean tau tilde composed with G. What does it do to x? This is what you get. And you compute G tau tilde, what it does to x, you get this thing. And you just compare these two expressions and you'll conclude that these two commute. Okay. Now, so where are we? We have this situation. So we have D is in K star modulo K star to the power. And let me write omega here to say that it's in the omega subspace, omega eigenspace of this, right? From such a D, we got this extension K, pth root of D over K. And we have seen that this is commutative. Abelian, as it's called. I mean, the group is commutative, so the extension is called abelian. This is abelian. This is of degree P, and this is of degree D, where D divides P minus 1. In particular, D is, or GCD of D and this GCD of these two things and P is equal to 1. Now I have this purely algebraic fact about finite groups. If I have a group, in fact, okay, in this case it's even commutative. So if I have commutative group G, a subgroup H, and the quotient is Q, so that's an exact sequence of finite commutative groups, and the orders of the subgroup and the quotient are relatively prime, which of course means that the GCD of these two things is equal to 1. Then this sequence admits a section. Not only does it admit a section, it admits a unique section. In other words, I mean, I'm not saying anything very, I mean, you just need to figure out what's going on here. So what it means basically is that G is equal to H times Q. That's all. Okay. So now what? So what? So what does this group theory result give us? What it gives us is that in this situation, our group here is now going to be, let's call this group G. Then, okay, it was called H, so let's continue to call it H. In the lemma, it's called H. So if this is H and this is, what is it? This is delta and this is G, then I have this GH, G delta. This is of order P, this is of order D dividing P minus 1. Therefore, they are relatively prime, and therefore G is equal to H cross delta. And then I can take this, if this is L, I can take L. LH is of course equal to K, but I can take L delta. That's going to be a degree P. This is a degree P cyclic extension, such that this L delta upon this degree P cyclic extension gives back D. In other words, we have shown that degree P cyclic extensions of F, they are in bijection with the omega eigenspace or lines, FP lines in the omega eigenspace of K star modulo K star to the power P. This is what we have proved. So here is the summary. Take any field of characteristic different from P. P is a prime. Adjoin a pth root of unity to F to get the field K. Delta is a Galois group. It comes with a character omega into Fp star, right? Giving the action on the pth roots of unity. And the thing is that the cyclic extensions of F of degree P are in canonical bijection with the set of delta stable Fp lines in this space on which delta acts through omega. So the subspace of K star modulo K star to the P power P, this is an Fp space, right? The subspace on which delta acts through omega is called the omega eigenspace, and sometimes written like this with omega in the parenthesis here. So this is for F any field, right? This is a purely algebraic result. Now we have to get back to our finite extension of QP and determine the omega eigenspace in this case. Okay, so let me just take 1 minute to see if there is any question. Okay, if there are no questions, let's continue. Right, so I have my finite extension of QP, and then I adjoin a primitive pth root of unity to get K. I have the group delta, I have the cyclotomic character omega. So that's all there, but can we determine what is the degree of K over F? What is the ramification in index? What is the residual degree? Of course, the residual degree is going to be the degree divided by the ramification index. So we just need to find out these two things in order to find out what the three things are. So in order to determine this degree and the ramification index, we recall that F zeta, when I adjoin zeta, a primitive pth root of unity, that's the same as adjoining a p minus 1th root of minus p. Remember, we had proved that if you adjoin a pth root of unity to QP, that's the same as you adjoin a p minus 1th root of minus p. Okay, so I recall that. So the degree is, of course, just going to be the order of minus p in this group f star modulo f star to the p minus 1. This is again by Kumar theory, right? Kumar, because f contains a primitive p minus 1th root of 1, of course, right? Even QP star contains such a thing, right? And the ramification index is going to be the smallest integer s such that minus 1 bar to the power s belongs to this subgroup of this. F star modulo f star to the power p minus 1 is a certain group. I think of kf star as a subgroup of f star. Strictly speaking, it's omega of kf star, which is a subgroup of f star. It's a subgroup of it's a subgroup of OF star, which is a subgroup of F star, right? But I'm sort of identifying KF star with its image in OF star. This cannot lead to any confusion. Okay, so this, so basically the ramification index E K over F is equal to the order of, is equal to the smallest integer S, such that, yeah, this here it is, smallest integer S such that minus P bar to the power S is in this subgroup. And here is a small proof that just uses the fact that, when I adjoin, when N is prime to P, and when I adjoin nth root of some A to my F, this is going to be, and A is unit, then this is going to be unramified. So these are the kind of things that we are using. Okay. So now let's use this, introduce this notation. E1F is going to be EF. That's the absolute ramification index. The full name is EF, E of F over QP. I'll just call it EF. And when I divide it by P minus 1, I'll call it E1F. So similarly, E1K is going to be EK divided by P minus 1. And it's E1F times S, because what is it? K F QP. So here EF is the ramification index, and here the ramification index is S. So this EK, of course, is equal to S times EF. And when you divide by P minus 1 on both sides, you get E1K is equal to S times E1F. And let's give it a name. The omega eigenspace for the action of delta on K star modulo K star to the power P, we'll call it V. Okay? So the first observation is that this space, which I've been earlier calling UPE1K bar, but now I want to show that no, it's the K has, I want to show it. This is to be, because when I write U1 bar, do I mean UK1 bar or UF1 bar or what? So I want to indicate K here, and therefore I'm writing these indices upstairs. So the lemma says that UK PE1K bar is containing V. And this V is containing, there should be a bar here, in UK1 bar, if this F is not equal to K. Of course, if F is equal to K, then it cannot be contained in UK1 bar. Okay, so let's prove that V is contained in UK1 bar. And so denote by VK bar the map which you get from the valuation. And the kernel of this VK bar is, of course, why is it VL here? Yeah, it's not L here. It's VK. Well, the kernel is precisely UK1 bar. And so if I have an X bar in V, and if I take a generator tau of delta, then tau of X is going to be what? X to the power omega tau, up to some pth power, right? That's what, because delta x on d through omega. That's what d, or on the whole of v, in fact, on the whole of v, it acts through this character. So x is in v bar. I mean, x is such that x bar is in v, and therefore you have this here, right? So let's just take the valuation of both sides here. The valuation of tau of x is, of course, equal to the valuation of x itself, because the valuation, why is it called L? Here, perhaps it's L is okay. L is here. Did I introduce this notation? L is this k, and you join a pth root of this x. That's the extension. Okay. So VL bar of tau x is going to be this. It follows from this, right? Is it L or is it K? I'm a little confused. Let's see. So it has to be tau of x. It's still in K, right? It's not L. So this, it is still, everything is still in K. So the point is this L is actually K. Yeah, Vk is delta invariant, and delta is the group here, right? Delta F, right? So here also it's not L, it's K. Okay, but F is different from K, and therefore this omega tau is not equal to 1, and therefore if the product of two things is equal to 0, then and the first thing is not 0, then this thing has to be 0, which is the same as saying that x bar has to be nu1 k bar. Okay, so I think these computations are not very enlightening, so I'll not perhaps give too much, I'll not go through the details. Fortunately, for example, for this one, I mean, it's somewhat complicated. I mean, 2-page computation. But it turns out that there's a fairly conceptual proof which just occurred to me while writing these notes. And this is the conceptual proof. So let me explain this. Let me explain. Let me find where it is. Yeah, so here, let me explain it here. So what I have to prove is that UKP E1 K bar is contained in V. This is what I have to prove. What we know is that this V lines here correspond to cyclic, so degree P extensions of F. Now, if I take the unramified extension, unramified degree P extension of F, that will give rise to some line in V. At the same time, so let's call it E. At the same time, EK over K is unramified, because this E was unramified over F, right? So ek over k is going to be unramified. And therefore, it will correspond to the line uk pe1 k bar. Huh? That's it. So that was the proof. So this line has to be there in V. Okay. So that this is a much more conceptual proof than all this here, which is, this computation is correct, but it's somewhat cumbersome and we don't need it. So here's a conceptual proof. I hope you have understood it. Let me just repeat it. I want to prove that a certain line is in this space V. Lines in this space V correspond to cyclic degree P extensions of F. Now there's the unramified cyclic degree P extension E of F, and the line corresponding to that has to be this one. That's it. So this line is contained in V. Okay. So the next thing I want to prove is that it may happen. See, K has been defined, K has been obtained from F by just adjoining a primitive pth root of unity. But it may contain a primitive p to the mth root of unity. A primitive p to the nth root of 1. That may happen. So if K contains a primitive p to the nth root of unity, but not a primitive p to the n plus 1th root of unity, then the image of this psi n bar in k star modulo k star to the power t, this will be a line which I'll denote by mu bar. So there's a subgroup generated by this, and the order is of course p. Okay, and the claim is that this line is also in V. So actually one can give, yeah, so maybe this proof works, but let me see. No, yeah, I think we have to go through this. So anyway, what we know is that tau of zeta is zeta to the power omega tau. That's how omega is defined. And this is what we have to prove. In order to show that omega mu bar is contained in V, this is what we have to prove, that tau of psi n bar is psi n bar to the power omega tau. Okay, so what is zeta? Zeta is psi n to the power p to the n minus 1. So tau of psi n, let's write it as psi n to the power g, and this g is some integer which is determined uniquely modulo p to the n, and it's prime to p. It's determined uniquely modulo p to the n because psi n is a primitive p to the nth root of unity. So on the one hand, tau of zeta is zeta to the power omega tau, and now I write back zeta equal to psi n to the power this, so that I get a certain expression. On the other hand, I can write this as psi n to the power p to the n minus 1 first, and then tau of, use that tau of psi n is equal to psi n to the power g. That's how g is defined. So this is one expression. Now I compare these two expressions. These two have to be equal. And therefore the exponents, the exponents don't have to be equal. They have to be equal modulo p to the n. But the exponent here is g times p to the n minus 1. The exponent here is omega tau times p to the n minus 1. So if they can be equal modulo p to the n only if g is congruent to omega tau modulo p. So that's the proof. Yeah, the proof, because that means that delta acts on mu bar through omega. This is what we have proved. And this implies that this mu bar is contained in V. Okay. So let's determine the filtration on V. And for that, I use the notation Vi is equal to this UKI intersected with V. We have seen that that this line is actually contained in V. So this one is equal to this. And this proposition says that, VPE1K is equal to VPE1K minus 1, minus 2, all the way up to minus S plus 1, where S, remember, is the ramification index of K over F. Now, how does one prove such a thing? So I'll now use the fact that lines in this space V correspond to cyclic degree P extensions of F. So take a line here, which is in PE1K minus F. A priori what I have is VPE1K is contained in VPE1K minus 1, which is contained in VPE1K minus 2, and so on all the way up to V. Of course, it continues. So what I'm proving is that you have actual equality. You have equality for at least up to this point. Okay. So let's prove this. Let's take a line D in one of these things. It's an FP line, which is not contained in the previous one. Then you get a degree P cyclic extension, right? Because they correspond to such lines D. And if T is the unique ramification break of E over F, then we have seen that the unique ramification break of EK over K occurs at ST. This is what we had done last time. When computing the, right, this is how actually T was computed. You first go to EK over K, you see what you get there, and then you compute. Yeah, so I think we had used the transitivity formula for the different. Anyway, so, but we also know that for EK over K, the unique ramification break occurs at PE1 minus this index, whatever this index is. So minus this index here. So that turns out to be I. But ST cannot be equal to I because I is between 1 and S. This is S or 2S or so on. And here is an integer which is less than S minus 1. So the only way out is to conclude that there is no such line. Why? There's no such line which is in this space, but not in the previous one, which means that you have equalities all over here. But not when you come at the next stage S here. Here you had equality till S minus S plus 1, right? But when you come to minus S, it's of codimension FF. But FF is the you have KF, and this is an extension of FP, and this degree is FF. Yeah, right. So, so here's the proof that this is of degree F, degree FF. So okay, let me just give you an outline of the proof. It's a complete proof, but where is it? I think it's a somewhat long and complicated proof, right? Okay, so let me summarize this. Okay, let me summarize this. Yeah, so this is what we want to show. So this V PE1, let me just call it E1 instead of E1K, E1 minus S. This is containing U PE1 minus S bar, right? And then you have this subspace, which is V PE1 minus S plus 1. And of course, this is containing U PE1 minus S plus 1 bar. You have this square of inclusions, right? And in fact, this here, the lower left-hand corner, is the intersection of these two things in that thing. Therefore, this quotient VPE1 minus S upon VPE1 minus S plus 1, this is going to be contained in UPE1 minus S bar modulo UPE1 minus S plus 1 bar. Okay, this we know what it is. It's isomorphic to KK. And so inside this KK, we have to figure out what corresponds to this subspace. What is that subspace? And then we would know what the dimension of this one is. We want to show that this dimension is FF. The dimension of this one is FK, right? So the point of all this calculation is to show that this PE1 minus S modulo PE1 minus S plus 1 contain U PE1 minus S bar modulo U PE1 minus S plus 1 bar. This we have seen is isomorphic to KK. And we will show that this is KF inside KK. So we will find an isomorphism such that this gets identified. Oh, no, not here. We'll find an isomorphism here, right? This, such that under this isomorphism, this subspace gets identified with this. And that will complete the proof, because the dimension over FP of KF is equal to, of course, FF, right? So that's what we have to find an isomorphism here such that this gets identified with this. And that's, oh yeah, claim. This gets identified with, that's what is being done, right? It's right here. And okay, so how did this such an isomorphism come about? So to get an isomorphism like this, you need to choose a basis of, what is it? Pk to the power Pe1 minus S. Choose an appropriate basis, right? Not just any basis, but appropriate basis. And the whole point was that this here, which I've written down, is an okay basis of this, which does the trick for you. So first of all, why is it P times pi f? Pi f is a uniformizer of f. 1 minus zeta, and pi f inverse. Huh? Why is this an okay basis of this? Because if I compute the valuation of this thing here, is the valuation of P, what's it? Minus, as we know, minus the valuation of pi f, because there's an inverse here, and plus the valuation of 1 minus zeta. So the valuation of P is, of course, Ek by definition. And the valuation of pi f is the relative ramification index, which we have been calling S. And this is the valuation of 1 minus zeta is precisely E1k, right? Because you have, what is it? K, you have QP zeta, and you have QP. The degree, the ramification index here is P minus 1. The ramification index here is E1. So the product of these two things is E1, which is E, not E1 now. E K over Ek, right? Yeah, but Ek plus E1k is PE1k. So the whole thing is equal to this, and that's the exponent of this. So this element is actually an OK basis of this. Okay, and now this is a verification that under this isomorphism, this subspace gets identified with this. Okay, so here it is. This is KK, and the eigenspace is this becomes isomorphic to KF, and therefore the dimension is FF. So I'll skip the details now because I don't have the time, and it's not particularly enlightening. The idea is what is important. And you can check the details yourself. Huh? The notes are going to be available. It's perhaps a good idea to check them, right? And it's not just that it's not easy to do it when I can't see the people. Anyway, so let's continue. Let's take a prime P and take any integer E, put E1 equal to E divided by P minus 1, which is a rational number. And the claim is that there are E integers in this interval, 1 to PE1, which are prime to P. And these integers are B1, B2, BE, where BI is defined as I plus AI, and AI is the floor or the integer part. So if I have a real number X, then the floor of X is the largest integer. It's the largest integer which is less than X, right? That's right. Yeah. So this is just an exercise. It's not, you just write down these things and you'll convince yourself. And if somebody asks for a proof, you'll be able to supply it. It's a nice little formula for the sequence of integers which are prime to P. Okay, so the proposition says that for every I in this, here we had done it for B1, for I equal to 1. B1 is, of course, equal to 1. Let's just check that. B1 is supposed to be 1, that's I, plus the floor of 1 minus 1 upon P minus 1. The floor of 0 is 0, so that's 1. Okay, so the proposition says that the codimension here is also FF when I is arbitrary. I mean, I goes from 1 to EF. And the ones before that, you have equality. So we have seen the I equal to 1 case. We have done it in detail. The general case is similar, except that you use this as a uniform. This is an OK basis of this thing here. So it gives you an isomorphism. So what does this basis do? This basis gives an isomorphism of this quotient, or whatever it is. I think it should be UPE1K minus S times B to the I, right? That's the one. That's it. Bar. Modulo, the same thing. PE1K minus S times BI plus 1. So gives an isomorphism of this with KK, under which V PE1 minus S times B to the I modulo V PE1 K minus S B to the I plus 1 gets identified with KF. That's it. We wanted to compute the codimension here, right? This is what we want to compute, that it's FF. So if we do exactly as in the case I equal to 1, we have done it. We got an isomorphism with KK, under which the thing of interest to us got identified with KF, and therefore the codimension was FF. Okay. So the next proposition says that this when I take I equal to EF, right? EF is the ramification index of F over QP. When I take this, it's the whole of V. So earlier we had proved that V is contained in U1 bar, right? But now we are improving it and replacing this one by this this quantity which may be somewhat larger. And the proof is the same as before by considering what the ramification breaks of an extension, a cyclic degree P extension of F can be. So I'm going to omit it. I mean, it's not very enlightening. Okay. So what is the conclusion of all this? The conclusion is that if I take a finite extension of QP, which contains a primitive pth root of unity, and if I take the maximal abelian extension of K of exponent dividing P, and if I denote by G the Galois group, first of all, I mean, the observation is that this is finite degree over K. This is not true if K is a P field of characteristic P, M is the maximal abelian extension of K of exponent dividing P, then we have seen that the degree of M over K is infinite. Why? Because the dimension of K plus modulo P K plus is infinite, right? But here, when K is a finite extension of QP and I take the same maximal abelian extension of exponent dividing P, then I get a finite extension of K. And the proposition says that the upper ramification breaks of G, of this Galois group here, occur at -1, that's one thing. At all these integers between 1, these are in 1 and PE1K. These are the integers in this interval which are prime to P, and there are E1 of them, EK of them, yeah. There are these ek integers. Yeah, 1, 2 ek of them. And also at PE1k. That's where the ramification breaks occur for this maximal abelian extension of exponent dividing P. Why? Because we have proved that for such an extension, the upper ramification breaks, I said upper, yeah. The upper ramification breaks occur precisely at the unique ramification breaks of cyclic extensions of degree P contained in this M. So degree P cyclic extensions with a unique ramification break at T, then this T is either -1, this is the unramified case, right? Or it's one of the integers between 1 and PE1k, or which are prime to P, right? Or it could occur at PE1k itself. This last one, because zeta is there in K. Now, if I have an F, which is a finite extension of QP, which does not contain zeta, and I take the same maximal abelian extension of exponent dividing P, then of course, still G is a finite group. I mean, it's a Galois extension, and this is still finite because after all, a G is in some sense isomorphic to this, or dual more precisely, to this V, which is a subspace of K star modulo K star the P, and this is finite. Okay, so G is finite, and the upper ramification breaks occur at -1. This is the unramified case, and at these things, but not at PE1F. Of course, this need not be an integer, but even if this is an integer, no ramification break will occur here when zeta is not in F. Again, well, the same proof. And this is what I have been saying, that if you have a maximal abelian extension of exponent dividing P of a P field L, and it doesn't even have to be maximal. I mean, any abelian extension of exponent dividing P of a P field L, then the upper ramification breaks of the Galois group occur precisely at the ramification breaks of degree P cyclic extensions of L contained in M. Right? This is something which we had done on one of the previous occasions. Okay, so now I think we had computed this, that if F is a P field of characteristic P, then this left-hand side is the contribution of cyclic extensions to Serre's mass formula in degree P, right? Degree P here, cyclic. And Serre's mass formula talks about totally ramified extensions. So EL over F is also equal to P. And the terms were QF to the power minus CL over F, where CL over F, recall, is the exponent of the different minus P minus 1, which is what it would have been if it had been a tame extension of degree P. But there can be no tame extension of degree P, right? Right. So, and we had computed this sum and we arrived at this expression. What was the idea? The idea is that degree P cyclic extensions of F, they correspond to lines in F plus modulo P, F plus. And, and this has a filtration. So there's this line, the image of the ring of integers, then there's this, which is of dimension 1 plus F. FF is, what is FF? Is the degree of the residue field of F over FP. So it has this filtration, and you have this, whenever it's a multiple of P, you have equality. So the dimension of the first one is 1, the dimension of the next one is 1 plus F, and the dimension of the next one is 1 plus 2F, and so on, right? Except that these equalities one has to take into account. So this is a neat way of, so everything is so explicit that you can just compute the number of lines in each of these spaces which are not contained in the previous step, what the this exponent for each of these lines is, and so on. So that gives you the expression on the right-hand side. And to do the same thing for finite extensions of QP is now possible. So let's first see what happens when zeta is not contained in F. This is the expression you want to compute, as in the case of P fields of characteristic P. And the right-hand side now is the same as the previous one, except that this is the only difference. There it was I greater than 0. There, the summation, see, where is it? Yeah, here it is. But all the other remaining terms are precisely the same, these and this. And why does it get truncated here and not in the characteristic P case? Precisely because this V is finite dimensional. So it comes with this filtration, and I've renumbered it. I'm calling it W0, W1, WEF, which is the whole of V. And the codimension at each stage is equal to F, except at this stage where it is equal to 1. Right, yeah. And so if I take a line in Wi, which is not in Wi minus 1, for some I here, then the unique ramification break occurs at Bi, right? And so this is the, what is it? Yeah, this is the exponent of the different. And therefore, I mean, maybe should be able to compute this exponent C L over F. It's S L over F minus P minus 1, right? So it's P minus 1, and what is it? S over F. So this is minus times B to the I. That's it. So that's why you see this expression here. Well, that is one thing. So not only do you need to know this exponent CLF, but you need to know how many lines are there in I, which are not in Wi minus 1. And that is easy to answer because we know the dimension of these spaces, right? The dimension perhaps of Wi is maybe 1 plus FF or something. Yeah. So then you know how many lines it has and so on. Okay. The dimension over FP, of course. Finally, let's look at a finite extension K of QP, which contains a primitive Pth root of infinity. And I want to compute the same sum, the same contribution of totally ramified degree P cyclic extensions, and this is the same exponent. But now, in addition to the expression that I have here, in addition to this expression here, I have an extra term. This is the new term. Why is it there? That's because you don't terminate the summation here. You have to look at lines which are there in this space, which are not in U1 bar. Okay, so how many lines there are? There are so many, this many lines in K star bar, which are not in U1 bar. And the unique ramification break for these, for the corresponding degree P cyclic extensions, occurs at P times E1K. So S, the exponent of the different, is going to be P1, P minus 1 times this. This is the ramification break here. And so C is going to be, you subtract P minus 1. So you get this, and that's equal to this. So that's the exponent for each of these lines, and there are so many lines. So you just, this was the exponent. Yeah, here it is. And this is the number of lines, right? So you get this expression, which is what you find here, which is the new term here. Okay, so let me finish by giving you a definition, which, because this expression, this terminology might be useful somewhere. I mean, you should not get browbeaten by it. So when you have a P field K and a finite cyclic extension of degree P, and T is the unique ramification break, then we say that L over K is très ramifié. That's Serre's terminology. If this T is congruent to 0, is divisible by P. So what we have seen is that K has a très ramifié extension if and only if zeta belongs to K. And in particular, the characteristic of K is not P. And when zeta belongs to K, there are so many such extensions. Number of such extension is P this. For example, in if K is equal to QP zeta, then what is it? EK is equal to P minus 1. And QK, what is QK in this case? QK is equal to P, in fact, because this is totally ramified. And therefore, this is going to be P times P to the power, QK to the power P minus 1, whatever. So it's P to the power P, perhaps, right? So there are that many extensions. So when P is equal to 2, you have 2 to the, yeah, there are 4 extensions. That's correct. Yeah. Right. So let's finish here, unless there's some question from somebody. Are there any questions? No, if not, let's end this session and let's meet on Monday next week.